Okay, I'd like to go through Exam 5 in video here so that I can free up class time for some other activities. First, question 1. Here we have two electrodes. Here we're showing two electrodes and asking where the electric field is greatest. This should pick up on the lab that you did when you were using the poorly conducting paper and the silver electrodes painted on the paper. So the way to do this is to imagine what are the field lines going to be like, and then where are the field lines closest together, because that's where the field is the strongest. So field lines, recall, are going to be perpendicular from the surface of the electrodes themselves, because the electrodes, being conductors, are isopotential surfaces. And they're going to go quite near, so we're going to have something like this. And then very weak fields on the other spots. But basically you can see that the field is going to be strongest along the line connecting the two electrodes, so along this line, and closest to the round electrode, because that's where more of the field lines are going to be radiating away from that point. So C is definitely the spot that has the strongest electric field. For the next question, question 2, I had some illustrations on the page. I didn't copy them here. Basically, this is from the lab where you worked with the electrophorus and also with the electroscope. What we're describing is bringing a charged object, like a rubber balloon that's negatively charged, up next to a conducting plate that's neutral. When it does that, if you have a negative balloon, it's the negative charges that are mobile in a metal conductor. So it's going to drive the electrons to the opposite end of the plate. There'll be a dearth of electrons near the charged balloon. So when a person touches the opposite end of the plate, that grounds it, that takes the negative charges even farther away, removes the finger, leaves a shortage of electrons on the plate. So there's a net positive charge on the plate. So when you've removed the balloon, then the positive charges are going to distribute around the outside of the plate. So the final distribution will be that the positive charges are going to be on the surface of the plate and all around the surface. Number 3, we've got our positive and negative charges in a box. This question is a Gauss's law question. Gauss's law, recall, says that the flux through a closed surface is proportional to the charge enclosed within the surface. So we have to look for here the surface that encloses the most charge. This one's not it. This one encloses no charge. This one's not it. This encloses a positive and negative charge that comes to 0. This one encloses no charge. The only one that encloses any charge at all is the first one, and that's the one that has the greatest flux through the surface. Question 4. Large parallel metal sheets carrying opposite electric charges of equal magnitude separated by a distance of 44 millimeters. So this is essentially a capacitor, especially since it's got opposite charges. The electric field between them is uniform, right? That's what we expect for a capacitor. And it has a magnitude of 380 newtons per coulomb. So it's a uniform field, and that's its magnitude everywhere. And we know that it's going to be pointing from the positively charged plate to the negatively charged plate. But that's not what we're being asked. What we're being asked right now is which sheet is the higher potential, and that's just a matter of convention. Recall that potential is where a positive charge will have the highest potential energy. That will be next to a positively charged sheet, because the positively charged sheet is going to push it away. So it's going to take the most work to push it there from infinite separation. So it would be A, the sheet with a positive charge. B, now it's asking a quantitative question. What's the potential difference between the sheets? Well, that's the amount of work that it would take to push 1 coulomb from one sheet to the other. In this case, from the negative plate to the positive plate. And so what's that going to be? Well, it's 380 newtons per coulomb times 44 millimeters. Now 44 millimeters is 44 thousandths of a meter, so it's 0.044 meters. So if we do 380 times 0.044, we get 16.7, and the best one for that is 17 volts. Next question, the surface charge density, sigma. Now here, we remember that the formula for the field is sigma over epsilon naught. Since it's a uniform field, it doesn't matter where you are. Here we have to solve that for sigma. If sigma over epsilon naught is equal to 380 newtons per coulomb, then sigma has to be 380 newtons per coulomb times epsilon naught. What's epsilon naught? Well, we read that in the book. It's 8.85 times 10 to the minus 12 coulomb squared per Newton meter squared. So this is not it, because this is our 8.85 right away. So we need 380 times that. And I get 3.3 times 10 to the minus 9 coulombs per meter squared. So that would be C of these choices. That would be this one. Another Gauss's law question. We have a spherical Gaussian surface that encloses a point charge Q, and it's moved from the center, which is here, to a point off the center. So it's going from, starts here and ends up like this. And it's asking how the electric field at point P changes as it moves, and how the electric flux through the surface changes as it moves. Well, recall the electric flux through the surface depends only on the charge enclosed. And the charge enclosed isn't changing. It's moving around, but the total amount of charge enclosed is not changing. So the field, instead of being nice and symmetrical and the same at all points, is going to be different. It's going to be greater here and less here, but the total flux is still going to be the same. However, we already said that the electric field changes. As we move the source charge away from point P, then the field is going to get weaker. So the field will get weaker, and the flux will stay the same. Next, we have a potential diagram. This one's a little tricky because this is a potential diagram, but we're asking about an electron. We're putting an electron in here. The energies are given in electron volts, which is great because that enables us to see directly that for each volt that we've got on the electron changes its potential energy or its kinetic energy by 1 electron volt, so we don't have to worry about any weird conversions. It's saying that's released at x equals 5 centimeters, so that's right here, and with initial kinetic energy of 2 eV. Its potential energy is going to be the reverse of this plot, because this is electric potential. The potential energy is going to be electric potential times the charge. The charge is minus the elementary charge, because that's the charge of an electron. Where this goes up, the potential energy goes down. Where this goes down, the potential energy goes up. If we start here and add 2 eV, that means we're putting it on this line. So it's not constrained on the right, but it will be constrained on the left. So it'll have a turning point at x equals 3 centimeters, but it will not have a turning point when you go to the right. So how does it behave? It'll bounce off to the right. It can only go that far, but it's unconstrained on the right. Direction of the electric field at the following positions on the x-axis. So first here, that's 0 because there's 0 change in the potential. Now here, the potential is pushing the electron to the right. Here, again, 0 field, 0 direction. Here, now the potential is pushing it to the left. Not hard enough to trap it. We have to have much less kinetic energy for it to be trapped here. But nonetheless, it is pushing it to the left in this region. Over here at x equals 8 centimeters, then again, there is 0 electric field because there is 0 change in potential energy.